basically 0. It's 1 times 10 to the negative 10, right? It's basically, you cannot get, you didn't get 10 boys, did you? Of course you did, because you're not going to get 10 boys. What you'd have to do, essentially, is run this experiment 1 billion times, right? And then you'd expect, in one of those billion trials, you'd expect to get all boys. So if Chris walked into that store and bought 10 birds, and they were all boys, I would think something was up with the way they were sexing them, because there's almost no chance of getting all boys. What's the chance of getting 9 boys and 1 girl? I just did 6. 9 boys and 1 girl. What's the chance of getting 9 boys and 1 girl? Go ahead, say it.
9 to the negative 9.
It's basically 0 too, isn't it? It's the next one down. You guys are catching the scientific notation, correct? The 9e negative 9. That's 0.000000009. Of course, like, yes, that's a lot of zeros, which is essentially what the probability is. As a matter of fact, when does it actually start getting likely? When does it actually start getting likely, friends? How many girls?
Keep going down.
Keep going down. What's that right there? What's the chance of 6 girls and therefore 4 boys?
1%.
Roughly 1%. That shouldn't even happen. How about this? That's 7 girls and 3 boys, right? So now we're like almost 6%. Now we're starting to get into the realm of, okay, this could actually happen.
I think 8.
8, okay, boom. What do you think is going to be the mostest likeliest? Take a guess before we get down to it.
Well, it's been the same every single time we've done this. It's always the highest number that
Aha! But look at this one, Tabitha. Very, very good point, my friend. Very good point. Magic math. Tabitha made a very important statement. She said every time we've done it from 1 to 2 to 3 to 4, the last element was always the most likely outcome, the most likeliest outcome. But now it's not. What? Why is that? Why? Why is it? Why is the last one now not the most likeliest? I love that phrase. It sounds right to me now. Say that again, Jessa.
you have 10 selections, now you're 9 to 10.
Because the probability of a girl is 90%. That means on average, out of 10, 9 are girls. So the most likely outcome on average is going to be 9 girls with 1 boy. Now, it's not that much higher, but it is the highest. It is the highest. You guys buying this? That's why it's the most likeliest, because 90% of the time you get girls, which means out of the 10, there's going to be a boy on average and 9 girls. Fair enough?
Yeah.
So, what is it within the realm of possibility? I'd say these 3 possibilities are definitely high enough to be, you could expect most of the time between 8 and 10 birds. 7 is not out of the question. Once you get below 7, what percent of the time do you get between 7 and 10 birds? What percent of the time do you get between 7 and 10 birds?
Whenever you go
Roughly.
by 7 and 10. You mean female?
Excuse me, girls. Thank you, Tabitha. Yes, girls. A very good answer, by the way, whenever you go to buy 7 and 10. Yes, but what percent of the time do you get between 7 and 10 females? Thank you. Go ahead, friends. Now that Tabitha has corrected my English, and I appreciate that very much because I'm saying the wrong thing.
Like
99%.
About 99% of the time, right? Because, look, there's 1%, and everything below it is essentially 0. So you've got basically 1% of the time you're going to get 6 or fewer, which means the other 99-ish, I'm rounding here, I'm being a little cavalier with rounding, 99% of the time you're going to get between 7 and 10. Chris, how many girls did you get? They're all girls. So she fell in the 35%, the 35% range, which should happen. That's like 1 in 3. So every third time Carissa goes into the store to buy 10 birds, she'll walk out with 10 girls. That make sense? Who else has chickens? How big is the flock, Austin? 20! Do it! Love this. Let's build Austin's flock. Let's build Austin's flock. And we're also going to take a look at Austin's flock, too, on the graph. Smallest X, 0. Largest X, definitely 20. You can get all girls. It's done. Binomial, 0.9. Yes, very nice. Okay, thinking a little bit. It's done now. I'm going to take a look at it first, if you don't mind. Disc draw. Very nice. Good. Very good. Very good. Yes. There's Austin's distribution. What's the most likeliest number of girls? What's the most likeliest number of girls? Hopefully this makes sense.
18.
18. Why does that make sense, Chris?
90%.
Because 90% of 20 is 18. So on average, you should be shooting for roughly 18 out of the 20. So that's your highest point. Notice how 19 is pretty close to it too? And this is definitely a skewed distribution, right? It's horribly right-leaning, left-skewed. So the average is going to be below that 18, a smidge. Well, actually, it doesn't be exactly at 18, but it's pulled this way. Most of the data is actually to the right of the 18. You've got higher probabilities here and there than you do here and here, but they tail off so much that the average gets pulled that way. So, so what I love about this draw is you can really see the likely outcomes. They're the ones that are far off the horizontal axis. So 18 is for sure likely. So is 19, so is 20, so is 17, so is 16. How about 15? I think that's on the cusp of what usual is, right? Jess, you look at that and say, kind of go either way. You can always scroll over to it. You can always scroll over to it.
0.3.
Yep, about 3%, which is definitely, that's termed an outlier by probability standards. 3% means it's under the 5% cutoff. So that, again, one of those other definitions for outliers is anything that happens less than 5% of the time is unusual. So 15 would be unusual by that, although I could go either way with that one. I would say, it's small, but it's still on the part of the curve I can see. Does that make sense? But then you start getting to the ones that are clearly common. 9% of the time, 19% of the time. There's your 28.5, which is your most likeliest. Now notice that the most likeliest is still less than 30% of the time. So the most common probabilities, although they're the most common, they're also much smaller as the sample sizes get bigger. And why is that? That has to make sense, doesn't it? Why do they have to start dropping down as you get more and more birds in the flock?
Because your 10% grows every time.
Exactly. You're growing this way. So you have to distribute 100% across more and more pieces. So it has to be that way. There's no way for it not to be that way. Making sense-ish? And what's cool about this is you can also, like I said, run the one-bar stats on it. And you got your average up there at 18. You also get a standard deviation, although I tend to ignore that with heavily skewed data because it isn't the most elucidating thing when you have heavily skewed data. When should you be using your standard deviation? When you got that nice symmetry, that nice bellish shape. I mean, technically speaking, this is kind of a bellish shape if you ignore the entire left part of it. And we get into that in 244 in the tail end of this course. So as we will, week 10, we'll kind of deal with that in week 10 in here with an experiment that we'll run. But for right now, I just say ignore the standard deviation. Just look at the probabilities. If something happens frequently, then we can say we can expect it. If something happens infrequently, then we're not going to expect it on average. One more chicken flock? Who else? How many other chickens we got? How many you got?
7.
Jessica's got 7. Let's do 7.
Oh, chickens.
Yes. We're going to do a program. So what do you think 7 is going to look like as far as the distribution? Is it going to have that cool little bell up and down again?
No.
This goes back to what Tabitha was saying earlier. 0 to 7, binomial 0.9. Okay, it's done. You see what it's trying to do? It's trying to make the bell, but there aren't enough birds to do it. You see what it did? Remember how all the ones we did in class were ramped purely exponential looking distribution, ramping up like this. You see what this one's doing? It ramps up and then starts to come back as if it's trying to come back over and make the top of that bell that you don't get. That's because you're in that kind of middle between the 4 and the 10. At the 10, it starts going back off. At 20, it goes back over and starts to drop down even further. 7's kind of in the middle there. So there you go. Most likely number of birds is 7. And if you look at the distribution, you'll see why. And again, this is exactly why, Athena, I do not want you dealing with the distribution, because what numbers would there be in that row for the multipliers? 1, 7, something. And I don't remember what the something is. It's 7 choose 2, whatever that's equal to. It's 21. But that's the thing. Like, do you have to memorize that? No, I don't want you to. I don't want you to memorize that. It's like back in 105, dealing with the Powerball numbers. There's better ways to do it than by hand. Cool? Now notice it's just below 50-50 though. It's a crapshoot. This is interesting because Mike Smith, I don't know if you guys know Mike Smith down at the Cap Center. He's got 7 birds in his flock too. And he came to me and he's like, this is crap. I bought 7 birds and one's a boy. I'm like, well dude, I mean if you buy 7 birds, there's only a 50-50 shot that they're all girls. Actually a little bit less than 50-50. There's actually a pretty good chance you're going to get a boy in there. So he seemed upset about it because he got a boy. Math says you're probably going to get one. And then he felt better. And then, which, you got to brag about these makes people feel better.
Why is it bad?
Because usually it makes you feel
It
nauseous.
makes you realize that it's not someone else's fault. And
That it's just random chance.
Yeah.
But again, we suck at being random, right? We suck at being random. So it's nice to be able to kind of quantify randomness in some way. Fair? Believable? Who has a 7 in their flock? I'm sorry, who has a 7? Jen, how many boys and girls? Or was it all girls? 2 boys! What's the chance? 2 boys out of 7, what's the chance? What's the chance? Just about 1 in 8. Right there, 12.4%, just about 1 in 8. What do you guys think? That's small, but not so small that it's, I mean, obviously it happened, right? But not so small that if she got 2 girls and 5 boys, I'd be like, okay, where'd you get these guys from? But 2 boys and 12 girls, it's definitely within the realm of 95%, right? 95% of the time, you're going to be in there somewhere. Cool? I'm just adding these quick tabs, like 47 plus 37 plus.
That's what you would do with the rooster.
Oh, she's wondering with practicality. What did you do with them?
Oh, okay.
You remember?
Yeah.
Yeah. I mean, Craigslist is full of roosters being given away, and then I'm sure they make good soup too.
Yeah, great soup.
Just don't name them.
How long does it
Yeah,
take
what's
to
the
find
name
out
of
it's a
the
rooster?
I've never had one. How long, Austin? Do you have any in your flock? I'm assuming you did.
We only got 2 of them, but they're a lot bigger than the other ones.
Oh, they develop more quickly, don't they?
We're just kind of assuming that they're roosters because the other ones are still pretty like small on the roosters.
Oh, so you got them this year.
yeah,
You just got the birds this year. Oh, right. Beginning of April, they usually put them out as day olds. They get these big spikes on the back, big spurs, and they get very aggressive. Tail feathers, yes, tail feathers. Yeah, they get very aggressive when you get near the girls.
I just have to throw in, it doesn't matter if you name them. We had chickens and roosters are so mean, you will gladly eat them.
You're gonna be delicious.
Like, you take that, Roger.
Mary, now I'm gonna call Martin. Yeah, yeah. Delicious.
See you, Roger. in the
Fried rooster. Same ring to it.
chicken and dumpling.
Say, who?
Chicken and dumpling.
Chicken
Roger.
dumplings?
That's all.
Those same bird, I guess. So Austin, you got 2 boys and 18 girls.
Yeah.
So he got exactly what he's supposed to get on average. Pretty cool, huh? Pretty cool. All right. Now, friends,
Huh?
let's turn this off for a sec. I want to come back to it. But what I want to make sure you guys realize is not everything that's an experiment is a binomial experiment. These are. Chickens are. And what I love about the chicken experiment is that, there's Mike. What I love about the chicken experiment is I can refer to that in 244 and students go, oh yes, 90-10. It's a coin. It's flipping a coin. A binomial experiment is always flipping a coin. But it's not always 50-50. Does that make sense? So the coins are weighted differently depending on what you're studying. Sometimes it's 50-50. Chickens are 90-10, right? Or 95-5. Sometimes I've been told that chickens are identified 95% of the time correctly. But if it's a coin, it's binomial. So think of that. A binomial distribution is like a coin. Not necessarily 50-50, but if it can represent it as a coin. Tabitha, you got a question. Go ahead.
No, I was just gonna say it has to have 2 variables of interest.
It has to have one variable that can go 2 ways.
That could be, okay.
Right. So and that's like a coin can go heads or tails.
But the percentages are different.
But the percentages could be different. Sometimes you want a 50-50, we'll see one here in a minute, where you want a 50-50 to compare it to. But they don't have to be 50-50. For example, the chance of breaking your leg at Mount Bachelor. I think I used this one in class yesterday. Oh, it was a 105. It was a 105. It was, you know, what do you think the chance of breaking your leg at Mount Bachelor is? Going up there, assuming you're skiing. Not snowboarding, not jumping, just skiing, like old man skiing like me. Downhill skiing. Give me a number. Give me a number.
300.
I said 2%.
2%. 2% 98. 98 2. There's your coin. 98 and 2. You can assume it's a binomial experiment if you study, say, 20 people. Because so many people go to Bachelor every day, if you pull 20 of them, you can treat them as independent events. And you can assume that if I break my leg, that doesn't affect somebody else. And I'm going to speak more carefully now. You're going to assume that I'm going to break my leg and something else is going to. Does that make sense? What I'm getting at here, friends? What's the chance of dying with a sneaker wave on the Oregon coast? Much higher than you think it is. I just learned this past weekend going to that Tesla show. Apparently, like 2 to 3 people die a year.
Oh, what wave?
Sneaker waves. Those crazy rogue high tide waves. They just come up. You're playing on logs. The Oregon coast has these huge driftwood logs. People playing around. Blah, 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 blah. This big wave goes up, clobbers you, get stuck on a log, pulls you out. Apparently 2 to 3 people die every year. But it's still binomial. You either die or you don't. I mean, honestly, it's binomial. So what I want to do is, I want to look at some experiments and have you guys tell me, are they binomial or not? Here's one. Roll a die one time. Count the number of pips you got, or the number. Give me the numbers on the dice.
No.
No.
I hear no. Because it's not a coin flip, is it?
No.
It's a six-sided coin, which is not a two-sided coin. So that is not a binomial. Okay. How about this one?
Yeah. Yeah.
Okay, gotta go for yes. Second for
Yes.
yes. All in favor?
You got
Yeah.
one number or all the others?
Yes, you can make it binomial by betting on one of them. Now it is a two-sided coin. What are the odds? What are the odds and sides? 1/6 to 5/6, right? You got a 1/6 chance of getting a 3. You got a 5/6 chance of not. So the coin is 5 times heavier on one side than the other. That's the definition of odds, by the way, which I don't talk about too much in here because most odds are Vegas odds, they're set by bookies. That's the mathematical odds. 5 to 1 against odds right there, betting on 3. Okay, here we go. Let's do a couple more. Next up, pair of dice. Pair of dice. Rolling 2 dice, 1 time. So fixed number of trials. And summing the pips, like you did in class.
No.
No, because that's how many sided coin? That was a terrible
12?
statement. 11 actually. 2 to 6 sided
Oh, yeah.
coin. 2 to 12, 11. 11 sided coin. Not a good. How about this one?
What would that be? 3?
Well,
Yeah, 'cause you got
you can
some
set it
eleven.
for
Wait,
11.
four.
and
Yeah.
So, I hear people saying actually a 3-sided coin, but if you're betting on 7 or 11, you're either going to win or you're not going to win.
Yeah.
Binomial. You're going to win if you hit 7 or 11. You're going to lose if you don't. So you can make it, some of you are saying, no, it's not binomial. I don't doubt. You can say it's not and call it trinomial. That's totally fine. But I'm saying you can treat that as a binomial because you either, say that again?
Because you're betting.
Because you're betting either going to win or you're going to lose.
Okay.
Does that make sense?
Yeah.
How about the weights of yeah. It's like the most unconvincing yeah ever. How about the weights of the coins and the sides? How about the weights? How much does the win side weigh of the coin? Either win or lose, right?
Light.
So it's light. How light? Define light. How light is that win side? How often do you win?
2 out of
420.
136.
I love this. It's out of 36, isn't it? It's out of 36. How many ways can you roll 7? Do you remember?
There was a lot.
There was it's the most common. Close. 6.
8 out of 36.
Good. The whole probability is 8 in 36. There are 2 ways to roll an 11 and 6 ways to roll a 7. So it's 8 out of 36. Fairly light, roughly 25%-ish, somewhere in that neighborhood. So pretty light. But that is binomial. You can treat it as binomial as such. Is that fair?
Yeah.
You guys buy that? Okay, good. Here we go.
Do we buy that? It makes me think that you're trying to convince us something that isn't.
I'm trying to convince you that it's correct. I'm just trying to, what I like to see is, I like to see students go, okay, I'm convinced because mathematically it makes sense. I'm not trying to like twist your arm into believing that like Tesla's the greatest rock band of all time, because that's an opinion. This is just a fact. Like it is, how about this one? 2 dice, rolling 7 11 each time. Or betting on 7 11 each time, I should say. Is it binomial?
No.
Oh, how come?
You're rolling
You're rolling
5
five
times.
times.
Yeah.
But that's a fixed number of trials, right? I'm saying, well, I'm going to play 5 times. So I'm going to bet. So as long as it's a fixed number of trials, it's like
It's like
having,
playing 5 games.
it's like having 5
You're not
chickens
saying that-
in your farm. It's like buying, each time you play, you have an 8 in 36 chance of winning, correct?
Okay.
Each time you play, you've got an 8.
change every time you play the game.
It's still 8 in 36. So it's constant probabilities. It's just like Max going in and buying birds.
Yeah.
Every time he reaches in to grab a bird, there's a constant probability of boy or girl. So him reaching in to grab a bird is like you throwing a pair of dice, and I'm sending him in 5 times. Is that fair?
Fair.
Yeah. The key is that it's a fixed number of trials. I'm not saying play the game until you win 5 times. That's a different story, isn't it?
Yes.
Because that could take any number of trials to win 5 times. I'm saying play the game 5 times, bet on 7 or 11 each time. Probability stay the same, fixed number of trials. I don't know.
Buying it.
Yep, good. Fair enough? All right, here we go. Let's switch over to a 244-ish kind of thing.
Well,
Is this a binomial experiment?
yes.
Beth is nodding yes. Tabitha is seconding that. Convince me that's binomial.
You're either colorblind or you're not.
Okay, boom, we got the by part. Either you're colorblind or you're not. So we'll definitely have 2 outcomes there. Good. What else is a binomial?
You only have 20 people.
I've said it to 20 people. I bought 20 chickens. Austin left, but we just built this flock.
You have a closed sample.
We have, say that again.
A closed sample.
Just define that for me, Raphael. I love that.
Well, basically, you're not leaving it open. You're not adding.
Oh, that's what you mean. So 20. You've stopped it at
You
20.
stop at
Thank you.
20,
Perfect.
That's how you do
Yeah, that's another way of closed sample versus an open-ended sample. I like that very much. Good terminology. What's the one part we haven't mentioned yet?
7%.
The 7%? How do we know it's staying 7% from trial to trial? If I take a guy out of the pot, doesn't that change the percentage of the guys that are left? Cedar, what are you thinking?
Taking one out doesn't affect the probability of the recipe.
There's 150 million guys in America. Pulling one out, whether he has color blindness or not, is not changing that 7% in a measurable way. Exactly. Arguably independent, as Athena said earlier today. Arguably independent. Fair? Good? Good? Okay, good. Let's change the experiment a smidge. Change the experiment a smidge.
No, because you keep selecting at random. There's not a constant.
Just let it piss. No. No, damn it, rule.
There's not fixed number.
So the problem here, we've matched the binomial part, have or don't. We've matched the 7%, and the 7%, chances are, is going to stay 7% regardless. But the problem is, what's our largest x, if you will? Theoretically speaking, there is no largest x. You might have to select. You may have to select hundreds, if not thousands, of guys in order to get 20 that have red-green color blindness. And only 7% of the population has it. You see what I'm saying?
Yeah.
So there's no closed sample as Raphael. This is an open sample. We have not fixed the number of trials. We've fixed the number of successes, which is a good distribution. It's called a geometric distribution, and it's very useful in a lot of ways. For example, when people are building robot arms to build components, like building iPads and iPods and things like that, if certain parts are automated of the process line, you've got robot arms doing things, you want to make sure that robot arm gets its job done, say, within 3 tries. If it doesn't get it done within 3 tries, then the part goes through without being finished, like put the door on the car. It's 3 tries to put the door on the car. If it doesn't, your car doesn't have a door. That's a bit of a problem. Bit of a problem, unless you don't want doors in your car. So you want to make sure that there's a high probability that the door gets on the car within 3 tries. But that's not binomial. That's one of these things, geometric. But again, you guys don't have to care about that because we're not building cars. Okay, here we go. Fixing the trials again. Fixing the trials again. Fixing it to 10. Okay. 10 trials. Okay. What say we? Is a binomial?
Yes.
Think Athena and what she said earlier. What did she say earlier? What did she mention about independence of trials, which is a big one? What was that word you used? Oh, I mean, it's wonderful. None of these trials that we talk about today are independent, but they are.
Easier.
Oh, good, good. But because they're independent, they're easier to calculate. But why were we allowed to assume they're independent? It goes back to something what Cedar just said too. Large population, tiny sample drawn from a large population, arguably independent. What's the problem with this? Think about how many guys are in this class.
You have to have 1/10. You have to have a
Hey.
10, not a 7. So you can't chop somebody into one eye.
You can on average. You can on average, Athena. No, don't revert back to a math student on me. Don't revert back to a math student on me, sister. You're still a stat student. Still in a real stat class. You can't have 0.7 of a person, but you can average 0.7 of a person. Forget that. Forget that. Suppose you only have, say, 20 guys in the room.
Okay.
As soon as you take one out, you have measurably changed the population. You've removed 5% of it. When you grab another one, you've removed essentially even more than 5% of that remains. We can't use the arguable independent bit anymore because the arguably independent thing is not true. It's only true, as Corey said, small sample, large population. This is basically a large sample and a small population, if you think of it from a percentage point of view. So that would be a hypergeometric distribution, which is fantastically fun. But you guys don't care about it because unless you really want to know where the Keno odds come from, you're not going to care. You guys analyzed it in 105 with Powerball. But you didn't realize what you were doing. I didn't call it, you did. I didn't call it the hypergeometric distribution then. We just crunched the numbers. All right, one more experiment for the day. One more experiment for the day. One more experiment for the day. See if you can see my experiment.
On each picture, too.
Can you see what the experiment is that I was interested in?
How many times to get his shoes on?
Okay, well, no. I saw this. So I saw it, this was like June, late June, early July.
Look at your experiment here with your child.
Well, I didn't tell him what I was doing. I'll share this with him when he's going to be over a beer when he's 21. But I told myself this is going to be fun. We're going to play with this in class at 2:43. So, I had to make it a binomial experiment. Which means what? Okay, that makes it the by part. It either has his shoes on the correct feet or he doesn't. In these 3 pictures, he doesn't. Okay. What else? What else makes it binomial?
How many times did you check?
Thank you. I checked exactly 10 times. I made sure to check exactly 10
Did
times.
you take pictures?
No, not every time. I tried to be as good as I can about not letting him know anything was up. And him being ADD and me being ADD was pretty easy. Just have a drive up here. Puts his Crocs on, go out and catch frogs in the pond. Nobody, usually off speed anyway. He wore Crocs all summer. That same pair of Crocs, he wore them out that summer. Okay, or he went barefoot. So, what I wanted to know was, does he put them on those feet because he thinks that's the correct, and I haven't told you the result of the other 7 experiments yet. Those are 3 pictures I took on 3 different days. The other 7 we'll reveal as we go. If I wait 10 times, if I watch him 10 times, randomly selected through the summer, I was pretty random about how I selected him through the summer. I made the assumption he's guessing. Because the first time I